and welcome to the release webinar for CENOS Radio Frequency version 3.0. I'm your host, Rainers, the product owner for CENOS Radio Frequency, and without further ado, we can begin the presentation. So, today's topics include the new results visualization, at least the added features that we have added to the existing ones. The second part will focus on the frequency step parallelization capabilities, which we added to increase the calculation speed. I'll get into that in a moment. And the third part would be the new computational algorithm. And afterwards, after the presentation, we'll be also holding a questions and answers section where you can ask any questions. You feel free to ask any questions in the chat, and we'll get to them at the end of the presentation. So let's start with improvements to the results visualization. So as you know, CENOS radio frequency has used ParaView up until this point to visualize the electric and magnetic field. And now we have already implemented this feature inside the inbuilt post-processing tool of CENOS. So you're no longer forced to use ParaView. You can do everything from the case setup to the results inside the software. And this includes the electric and magnetic field visualization. You're also able to slice the air domain to get the near field visualization. And we have also added some other features that weren't there before. So you may know that we had the ability to create create cuts of the 2D cuts of the 3D far field. And now you're able to position the cut wherever you want with the custom cutting functionality. We also made it possible to directly see the current density visualization when simulating real conductors, which previously was sort of a hidden feature within ParaView, but now that is also available in the inbuilt tool. And there have been some improvements to the user interface. So let me exit the slideshow and let me actually show you the results in the software. So let me share my screen. So now it should be visible. So this is the main splash screen of the software, and let me introduce you to our test subject in this case, which is a printed Yagi with the antenna on a PCB that's placed next to a conductive cube. In this case, it's simulating a cube satellite. And this is our test subject for the webinar. So let me go back to the desk and click on the eye icon to open the new results visualization. So we're immediately placed inside the charts, which is a result type that we had already before. But let's start off with the electric field visualization, which I can navigate through this tab. And as you can see, it automatically shows us the electric field distribution. So as we can see, we have the field visualization for the printed Yagi. And what I can do here now is I can do whatever I could potentially do in ParaView, which is to visualize the mesh. We can go through the frequency steps and visualize the changes in the electric field at each frequency step that we have simulated. I can also do it within the drop-down and find the specific frequency I want to visualize. You can also rescale the data range if you want to. So for example, I want it to be quite a bit less. And as you can see, the visualization does change. I can also change from the electric field visualization for the imaginary part and the real part and change the field component to visualize that. So for the electric field, that is it. You can also do the exact same for the magnetic field. So I am also able to change the parts and also rescale the visualization. And if we are talking about the near field visualization, what we can do now is what it basically does, it just creates a cut of the air domain around the model. And here I'm able to place the plane at which I'm visualizing the results at any given point that I want to. So I can rescale the visualization and see the electric field distribution around my design however I want to. I can also position the cut plane any way I want, and it's going to automatically replace the cut there. So that's how we can visualize the near field around the antenna. So the next part for me will be to show you the radiation pattern custom cutting. So as you can see, we currently have our free cut plane selections here, which corresponds to the planes of the uh, XYZ coordinate plane. And if I want to perform like a custom cut, all I would have to do is just go to the custom cut section. And as I did with the plane in the near field section, I can immediately create some cuts along the radiation pattern here. So I'm able to visualize that on the right side. If I want to change the reference pattern, so if I want to choose, for example, the radiation intensity, I can also change that and plot the radiation intensity that way. It's also possible to input a specific value. So for example, 50 theta and 30 phi, and plot that as well. So I can change it back to directivity, and that's how I would visualize it. You can also change the coordinate system to Cartesian if you want to as well. And the frequency step just changes at which frequency you are performing the cut. So as you can see, it automatically changes as well. So the last thing that I wanted to show you is the current density. So if you are simulating your case with real conductors, so as you can see, my IFA antenna here has defined the ground and the patch as a real conductor such as copper. In the results section, I am able to visualize the current density. So this result is also rescalable. Everything that you saw before with the electromagnetic field is also doable here. So the current density is also visualized. So that is actually it on the results visualization. So let me share again the presentation. And we can head on over to the next slide. So the next part would actually be the frequency step parallelization. So what this feature does, or what was the intention for it, is to introduce a way for us to create a much faster calculation. So how is this done? What we basically do is the user would, in the physics section under computational settings, so the section where you define the frequency, you are able to define a number. And this number directly corresponds with the amount of frequencies that are going to be calculated in parallel. So if I choose a frequency range from 2 gigahertz to 3 gigahertz with a step of 100 and select 2, it's going to divide that frequency range in 2, and one process is going to calculate from 2000 to 2500 to 2500 megahertz, and the other is going to calculate from that middle point 2500 to 3000. And that's actually basically it. So it's a significant speed up for small to medium sized cases. Um, in our testing, we saw up to 3 times faster, but your mileage may vary. If you have a stronger PC, you might actually see a much faster workflow. And yeah, one of few things that you do have to look out for, as this is currently a manual setup, you do have to make sure that your CPU can handle the multiple processes. So if you're running a larger case that's way in the 200,000 mesh element size, you may need to decrease the count to 1. And the larger the case, the more RAM you will need to calculate the case successfully and faster. So you may run into RAM insufficiency issues, or you may actually see a slowdown because the processes are all fighting for CPU time. So if I will show you how this works afterwards. And the next part is actually how we added the new computational algorithm. So we saw in a few cases, especially like RFID cases that have there are very low resonance structures, that we do need to increase the accuracy of the solver. And in these cases, we saw that there were some reflections or some calculation issues, which led to us increasing the basis function order. So this is how we actually achieve the accuracy in this case. And what we saw is that the accurate algorithm did produce much more lifelike results than the current, up until this release, default algorithm, which we have now dubbed as fast. It is the default setting in this case because there are a few things that you also have to take into account for the accurate algorithm, which is that it does require a lot more RAM. The mesh needs to be rougher than the fast algorithm, as the same mesh size will calculate for a longer time than the accurate algorithm. And it may seem that the calculation may be stuck, but I assure you that it's just taking a lot more time to define the calculation in the background. And that's actually it for the presentation. So let me showcase how the parallel processes actually work. So let me share my screen again. And in this case, we will also be taking the IFA case that I demonstrated earlier for the for the current density. So as you can see, the computational settings can be found in the physics section, right beneath the section where you define the frequency. So I can choose 20,000 to 2,500 with a frequency step of, let's say, 50. And we can keep the fast algorithm for now, but I can choose from one parallel process to two. And what we can do is just click run in this case. So since I did change the computational algorithm, it is asking me if I want to remesh. But if I were just to click run, it's just going to remesh it by itself. So let's click run, and let's overwrite the existing results. And in the case setup process, we can take a look at how the division of the labor actually happens. So as you can see, the parallel process 0 and process 1 started to set each frequency, and it calculates in parallel the frequency range. So in a moment, you'll see that it's going to head on over to the next step. But as you can see, I defined the frequency range from 2000 to 2500, and the second process starts in the middle. So if you go into the physics, we can verify that it's actually at that point. So it may be taking a little bit more time than expected, but that might be due to my presentation. But as you can see, it did cross over to the next step. And that's how the process goes. It just calculates in parallel. So yeah, while we wait, we can also set up the same case uh, with a single process and actually take a look at how quickly it would calculate. But basically, that's actually it for the presentation. And let me share the presentation again. This is a quick release webinar, but the features, well, they seem quite quite small. They have produced a significant improvement to the software overall. And here's actually a comparison between the fast and accurate algorithm on the left and the result paper for the Yagi case that you saw beforehand. So as you can see, there is a bit of a difference between the fast and the accurate algorithm, but the accurate algorithm, at least in the shape, closely matches the results that we see for the simulation, the measurement results on the right. And yeah, that's actually it for this webinar. So thank you for listening, and we can start the questionnaire. So if you have any questions, please raise your hand. I can also go back over to a previous step if I went it over too fast. Yes, Mike, go ahead. If you're talking, we cannot hear you, so you can also write your question um, in the chat. I see that you wrote, where does it show the RF source? Could you elaborate a little bit more? We can also take another question while Mike is writing his question. So if anyone has a question, please raise your hand.
Hello, is my audio working?
Yes, yes, it's
Again,
working.
my question is for a new person using the software. So if there's more experienced people, I'll let them go ahead with their question.
No one has raised their hand, so if this is regarding how you define the how you define the RF feed point, I can actually show you that.
Yeah, so if you
So
go
let me.
back to your first just first part of the presentation where you show where you can cut through the plane, I would just like to see where you actually have your feed point and how you define how you adjust your feed point, like your RF signals into the antenna.
So let me actually start with the IFA antenna. In the IFA antenna's case, we do the discrete port definition, meaning that you define two terminals to which you apply the alternating current.
Okay, got it. Okay.
But for the CubeSat case, let me go to the
Yes.
geometry here. It
Yeah.
actually does use a coaxial port definition. So it's fed with the coaxial port on the bottom, and as you can see, we have a coaxial port phase definition here. So the benefit of using the coaxial port is that it does not itself radiate, as shared sometimes with discrete port definitions. And the coaxial port actually blocks all the energy to the other side. So it's kind of
So
like
does
there's
the
like a back wall.
okay, so does a coaxial port it doesn't have an SWR of itself. It's assuming that it's an ideal source, an ideal connector, if you will.
I would say so, yes.
Okay.
You do
Okay.
define its own impedance, but sort of, yeah.
Okay, so the connector itself does not have a way, unless you model it separately, that it has a VSWR associated with it.
In this case, the geometry of the connector itself is assumed as a part of the antenna. So,
Okay, okay,
yeah, yeah.
okay, okay, okay,
So the connector itself, as it is a part of the antenna, it will affect the impedance of the antenna itself.
okay. And that's, yeah, okay. That's good to know. So it's included.
All right. If that question is answered, I see that we have a question in the chat. Um, I'm sorry, I won't try to pronounce her name in order to not butcher it. But one user is asking, is the parallelization available in the lowest tier hobbyist license? I'm not actually sure. I will have to double check with our sales team. So, Emil, if you are here, could you potentially answer this question?
I'm assuming that's Martin.
Martin is our marketing guy, but Emios is our head of sales and chief revenue officer. So seems that Emios is not available. I'm, I think deparallelization is not available in the community license. So, but I will have to double check with our team, and if you want, so we can let you know via email after the webinar. So, any other questions? Just a reminder for the people that did not make it to the beginning, this webinar has been recorded, and the webinar recording will be shared with you afterwards.
Hello?
Yes, wait to try.
Hello, hi. I only would like to test if everything is okay. And if you see me, I'm not so often using the Google. So I think I do not want to disturb with my question the all meeting, but I will be quite happy if we can share the ideas or my experiences which I have up to now with the things which will be discussed, I hope, in the seminar now.
We are actually at the end of the webinar right now. So this is the
Really?
question. Yeah. It was a quick one.
You're able to ask questions freely. Maybe
Yeah.
if you go through a small tutorial, if he has any questions, that would be good. Like I said, I haven't played with the software yet, so I'm curious to see how you can go through it.
That wasn't actually the plan for this webinar, and Wojciech is one of our more active users. So,
oh, okay. Well, then
yeah.
go ahead. I'm listening.
Yeah, okay. It's a pity because really I was just preparing to the webinar because it's local time, Central European, 16 o'clock, and I thought it will be beginning in 30 minutes, but so I missed the beginning and everything what was said on it. But okay. If you could only shortly remind me what you were speaking about, Reiners?
Yeah, let me bring up the presentation again. So today's topics were basically also in the release notes, which was the new results visualization, and quickly going over how it works, the frequency step parallelization capabilities, and the new computational algorithm, which is the accurate algorithm. So I shortly showed where to find each of these functionalities and how they work.
Yeah, okay. From my point of view, the new results of visualization with the software and how it works, yeah. Look, I'm not, or I do not want to be criticizing the thing. It's really perfect, and I like it. This is what I would like to stress on the beginning. There are some lacks with which I miss quite much. I discuss it with our common feedback. For example, as antenna guy or person who is playing with antennas, I would like very much to have the possibility to have somewhere the markers on the graphs and maybe to evaluate 3 dB beam widths and I think the zooming in the new plot visualization is quite rough or fresh, and you have to go outside of the window and return back sometimes to get it. But this is very yeah. Thank you for putting the windows here. In case of now, what I'm speaking about is the radiation patterns. If you have it into the 2D, it's very nice to be able to now to peak to maximum. This is and to have here something you do it by manual, and then to have a 3 dB beam width of the main lobe. This is the thing what's I think quite useful. And the 3 dB bandwidth should be, or maybe one dotted line 3 dB below the maximum, which would optically cross the diagram, because it's really not easy now to have here -3 dB line, which will go below the maximum.
Um, Going chronologically from your comments, you mentioned that the zooming functionality is a bit rough, but you don't have to go outside of the chart to zoom out. Sometimes there's a message here that appears. You just have to double click on the plot and it's going to bring you back home.
Yeah,
There's
okay, so
also
thank you for pointing that out.
you can also hide the visibility of specific lines if you have multiple lines in
Yes,
the
yes.
charts, and enable and disable the visibility. For the -3 dB lines and markers for the charts,
I
we
think
are
here in the XY graphs it works, but I think in the radiation pattern graphs the zooming out and in is, yeah, the double
yeah.
click. Yeah, that's the way. That's the way. But having somewhere the markers, even on the 2D or 3D plots, I think it will be a very nice functionality.
Definitely. We wanted to add markers for some time, but we did run into some technical difficulties with that feature. But we are still considering and trying to implement that as well. And thank you for noticing this issue, and we'll also take a look at that and try to fix it in the next versions. Um, I think we went over everything that you mentioned, or did I miss something?
Yeah, okay. Here, yeah, concerning we discussed the definitions with Brescia concerning the directivity and the gain. I think and radiation and intensity and the definitions. I think in a nowadays plotting, in most cases, the directivity and the gain are the same graphs without differences. I would like more have there not only the losses in the dielectrics, but the losses or implementation of lumped element losses as well in the structure, because, for example, you can have a losses in the wire, or even the traveling wave antennas, where the losses are necessary to bring the traveling or to start the traveling wave there. And the directivity of the antenna could be one number, and the gain could be another number.
It's typically the same number in cases where you don't have like conductor losses and the air domain is just vacuum. So in cases where you do have a lot of dielectric losses, you do see a much smaller value of the gain. But we still are working on the lumped element losses. So apologies from my side that it's taking a bit longer than expected, but we are still working on that.
Yeah, okay. I will be quite happy to see from you, like a specialist or author of the software, some ideas how to display the electric field, magnetic field, and near fields, and how to easily work with them, because in certain cases I was not able to get out any output plot of the fields. So I think Brescia give me some help with it, but if you could go this through, I will be quite happy if you didn't it before.
In this case, I would say that we should schedule a separate call
Yeah.
for this, but we can go quickly over how this would actually work for the IFA case, for example. So at least for my side, if I want to rescale the electric field, I would just use this functionality here. Apologies if I'm going a little bit too fast. If something is troubling you from the visualization standpoint, you can just click on the eyes to hide them. And yeah, for the near field, basically it's just clicking on the show plane and just moving the cut plane around. And the same goes for the rescaling. In this case, I would also choose a smaller value and rescale the visualization to get like a glimpse of how the
Yeah.
propagation happens around. And it's also possible to change the components of the fields. In this case, it looks like there's some overlap. Yeah, so that's how we get it.
Thanks. I'm not sure. Uh, Here, the graphs are looking quite nicely in case of the antenna without the electrics and not very concentrated places with the electrical field. It's not easy to get the visualization in scales uh, quite nicely because the gradient of the field is not so straight located somewhere, but it's more going far away. So I had a little bit difficulties, but I will go through what you explained in the presentation and find the way what I'm doing wrong.
Of course, we can also get in touch after the meeting and discuss this in more detail.
Yeah, thank you.
So yeah, if there aren't any other questions, I think we can. Yeah, go ahead.
Sorry, but I do not want to be here only speaking. To the paralyzation, if we can go.
Um, I did explain it in the first part of the webinar. So if there are
Okay.
any additional questions, you can send us a message, and we will explain it in more detail. All right. Seeing as how most of the people have already left, if there aren't any questions, I'll please stop the recording.